talk this morning. And Chris is originally from Australia, but he is a really scientific cosmopolitan, traveling around everywhere, right? So he has been for a while in England and for a while here in Norway, and he's now in Finland, living out in the forest and traveling in Danish Institute. And we're very happy that he has traveled all the way down here today. Chris is also very multidisciplinary, I guess that's the right English word. Many fields, covering many fields. Whenever I go to conferences, I think this is the most weird thing I've attended, but let's see the business. Chris is always there, so it's good to have people that don't know the wrong people. It's good to come here and tell us about things that has to do with astrobiology.
Thanks very much for that kind introduction. Alright, what I'm going to talk about today is a very specific issue in astrophysics, which I'll sort of broaden a little bit into astrobiology. So the idea is that there's mass extinctions and there's craterization on the Earth, and the small number of craters for which you can measure ages demonstrate a rather weak periodicity. And that period, one of those periods, there are several, the shortest one is around about 25 to 30 million years. So the astrophysical connection is there some connection between the orbit of the Sun in the galaxy and that period, which may or may not be present in the record at the Earth's surface. So I'll now go to the astrophysics of the problem, and that is what we want to do is measure how much matter is in the disk of the galaxy, and specifically what's the mass density, how many stars are near the Sun, and how much matter does it all add up to. And once you've figured that out, it's a simple matter to calculate how rapidly the Sun is moving in that mass potential. Alright, so the Milky Way is, we see the Milky Way from about 25,000 light years away, out here somewhere, and we look in and we see the bulge of the Milky Way and its disk. This is an infrared image, and it's about, the Milky Way in a sense is about 8 kiloparsecs from us, and it's about 600 parsecs thick. So this thickness of the Milky Way is what I refer to here. Now, of course, that thickness is simply caused by the fact that the stars are moving up and down. So in general, the stars take about, where the Sun is, they take about 200 million years to go all the way around, and they're sort of moving up and down like this. And this is accounting for the thickness of the disk. So that is what we'll return to this bobbing up and down motion, and that's the primary scientific result here. Now, in the as the Sun is moving up and down like this, it's passing through a higher density region and lower density region, and this is producing a tidal force. And the idea is that that tidal force can increase the number of comets which are coming from somewhere, the Oort cloud or further out. The number that come into the inner solar system increases during that period and decreases as the Sun is moving around on this orbit. So starting from now, the background density of matter around the Sun would be increasing and decreasing on this cycle about 30 million years. The number of actually very accurately measured ages for craters is very small. So we're talking only about a handful or so. So here's a list, and obviously this one's one of the more interesting ones at 65 million years. These are really just a handful of craters for which accurate ages are measured. If you throw in all the other ones as well, you can get a sample of about 30. And then by running it through various statistical treatments, you come up with various periodicities which are in there. You've got 30 events, 30 age measurements. So the significance of these periods as measured is really pretty weak. And the range of them that come through are something like 25 to 30, I think you can fairly say that. But you can see that there's quite a scatter. Depends how you treat the data, which ones you decided good and which ones you decided bad. You can restrict yourself to certain sizes of the crater. You can go to other, not to craters, but to extinction of fauna and so forth. The range that's talked about is 25 to 30 million years. Okay, so let's return to this astrophysical issue. So the Sun, a typical star in the disk of the galaxy, is moving upwards with sort of 10 to 20 kilometers per second, and will rise some 100 to 300 parsecs above the disk before turning back. So that is of course completely controlled by the amount of matter that's in the disk, and that's a method you can use to measure the mass of the disk. Well, you can look at one star for a few million years, or you can look at a few hundred or a few thousand tracer stars for a few years. And looking straight up helps a lot, because all you need to do is measure the radial velocity of the star, which is very straightforward, and that tells you how fast it's moving up and down. So, in short, by measuring the vertical density distribution of stars and the kinetic energy, radial velocity of the stars, the balance of those two is just the balance between potential energy and kinetic energy, and that's how you can reconstruct what the amount of matter is in this the galaxy. And it's important to remember that this measures all the matter that's there, so it's a measure of gravity, so you see everything in such a measurement, and you can compare that to what you can actually see. You can count up all the stars and all the gas that you can actually see. And so for a long time in astronomy, this was a big issue, because the amount that you measured was about twice what you could see. So, and that measurement went back to the 1930s when it was done for the first time. It's a really classical issue. And still until about 15 years ago, there was still disagreement about have we seen everything in the disk of the galaxy. This is one of these dark matter problems. So about 15 years ago, we started work on this, and I'm happy to say that we finished last year. So it's one of the longest running projects we've worked on. So what we do, this is our galaxy today, and the Sun is sitting out here, black center is here, and you make a sample of stars near the Sun, and you make a sample sticking up out, and just count how many stars are up there and measure their velocities. The kind of star which we used just for the astronomers here, so this is the classical heptameral diagram. Giant stars are over here, and these are the main sequence stars, and we were using this kind of star. There are lots of them. They occur in all kinds of what's called stellar populations, and they're easy to work with, bright and easy to work with. So it actually started out on this telescope, the Oddie, which is a classic, beautiful brass and clockwork telescope, which was installed with an astronomer in 1911, but unfortunately in the bushfires last year, it was one of the victims, so that's what its present state is right now. But this is one of the ones that they're planning to rebuild on the mountain. Okay, so it was the 80s when this stuff this whole issue was attacked in the 80s, so you can sort of live with a factor of 2 in astronomy for about, from the 30s to the 60s, factor of 2 was normal. Then this dark matter problem came. The whole galaxy seemed to be not just a factor of 2, but now a factor of 10. The whole galaxy had dark matter problem, and this became widespread in astronomy in particular. So it became rather more interesting to really be absolutely certain, have we understood how much we can really see in our galaxy? So that was why there was a big push in the 80s and 90s to do this again. So what one's measuring is how many solar masses of material does one see in a square parsec of the disk, integrating all the way up and all the way down. And the numbers that were coming through were from sort of 50 to about 80 solar masses. Now this is not yet good enough to calculate the orbit of the Sun with any accuracy. Now these were prior to the flying of the Hipparcos, the European Space Agency's Hipparcos satellite. And what it did was improve things enormously by measuring the distances to nearby stars, so you could really count them up properly nearby. But also you could make much better calibrations of how far away more distant stars are. And that was a key ingredient in this new work. So we dragged out all this stuff, which was sort of been lying around from 50 years ago, and redid the whole thing based on these new Hipparcos results. What you do is start from what you know. So you make a potential from the matter that you can actually see in the galaxy. So it consists of the local density of gas and main sequence stars and all the other kinds of stars, stars which never really form properly round dwarfs, white dwarfs are dead stars, and so on. And we also incorporated space telescope work because with space telescope you could see one could count very faint stars much better than from the ground. So you can actually tell the difference between a star and a galaxy with a space telescope, which you couldn't do from the ground. And this allowed us to count the number of extremely faint stars in the galaxy. Finally, it could be done. That was another key development. So putting all that together, one makes a model of what the matter in the disk looks like. So you start, this is the center of the disk. It goes up to about 3,000 light years above. And you have a gaseous component, which is rather thin, falling off. You have a young stars component like this, older stars component like this, and then the whole thing is adding up to something like this. And the total is adding up to about a tenth of a solar mass per cubic pascal. And that's all the matter we actually know about. The question is, do these older observations, can they be made to fit with that particular distribution of matter? So you've got the matter, you've got the stars floating up and down inside this thing. You can calculate what their density should be, and you can calculate how many of them you should see in a particular sample as you look up. Here, the data points are the sample, and the line is a prediction. It's not fit. It's just a prediction from the model, and it comes out very nicely. So what it's telling you straight away is that all the matter you can see is all the matter. Now, if you threw in some more, the whole galaxy would simply get, the stars have to work against more potential energy, so it would just get thinner. The number of stars in the sample would drop away that you're looking for in this, as you're looking up. And that would be one example of how that would be. If you added twice as much matter there in some kind of dark component, then you would drop away like that. But anyway, this is a completely satisfactory fit with the matter that we know of. Okay, so now that you've got a model for the matter distribution, you can calculate the acceleration of the star. So in 3,000 light years going up, this is the acceleration that a star will feel as it's going up in this matter distribution. In fact, within about 100 parsecs, it's pretty close to linear. So any star moving in this potential will be pretty much executing simple harmonic oscillation. And this turns out to be what the sun is doing. So the sun in this potential will be going up and down with a period of about 85 million years. You can see that here. This is the distance of the sun above the disk and below the disk. It's about an amplitude of about 100 parsecs. So it's oscillating up and down with this period, 8 million years. One can, and this with less precision, one can construct a model for the whole galaxy, basing it on, you made a measurement of the amount of matter near the sun. So the sun, this is the central galaxy, and we're looking at it from the top. Here's the position of the sun now. So the sun is moving in a particular direction with a particular speed and starting from a particular place. So we can just calculate the orbit on the whole model of the galaxy. So it's in a quite circular, the sun is in a very surprisingly circular orbit going around. Here it's about 200 million years. So this oscillation period is rather long. It's 85 million, so the half period is about 42 million years. And we can put a number on, now finally put some kind of error on this, of that 3 million years. So its distance is going up about 100 parsecs, oscillating on a half period of about 42 million years. So this is the point, as it passes through the galactic disk, the orbital comets will get a bump in the tidal wars, and then it will get another one when you come here, and then things will calm down, and so on. So it's pretty clear that 42 million years is hardly consistent with these planned periodices in the extinction and cessation record, crediting record. Oh, okay. So that's the main conclusion of this first part of the talk, is that these periods which have been suggested have often been associated with the possibility that it's just simply connected to some sort of, but I think that that evidence is quite weak, and certainly the weak point in it at the moment is that this period is very poor measured, but finally this period has been measured with some points. Alright, we'll move on to a second topic, and that's this galactic habitable zone, which came out in Science paper just a week ago, lightly very tough. And I'll just say a few words about this because I was in Melbourne, 2 of our authors were in Melbourne, I was working for a year in 2002. I just wanted to give them some credit about this, so I'm kind of with the message. So the idea is that there's a light hospitable zone in the galaxy, and it's quite similar to this, what used to be thought of as the circumstellar habitable zone. So if you look in the older text, you always see this sort of ring where light is supposed to be best suited to surviving in the solar system. But actually, one probably wouldn't take that so seriously anymore because there are many environments scattered all around the place where one can presumably were big body actually looking for life in the solar system. But there's an analogous zone in the galaxy. So this was suggested by Gonzalez in 2009. I understood from Wolf yesterday that that's the reason he's cancelled his scientific community. So it's written, I wonder whether there are any more of us. Okay, so the galaxy, we see it from the side over here and from the top here. It's a kind of zone around this part here. So what it basically boils down to is you need metals in order to form planets, and there's a metallicity gradient in the sense of the metals are building up in the galaxy in a particular way, and that gives you a selection of metals. The second thing is that you need sufficient time for biological evolution, which took 4 gigayears, for complex life, it took 4 gigayears on the Earth, but this is not a critical assumption. And the other thing is you don't want too many supernovae destroying life at varying conditions. At the site where the particular lactocentric radius that you're talking about. So what they've done is added this standard galaxy formation models to the picture just to see how it runs through. It's a kind of model. But you have a standard galaxy formation model where the gas is all sort of settled in. You start churning away, making stars. More gas is coming in all the time. So basically, it's already been set up. The disk is nicely constructed and it's just slowly bubbling away for sort of 10 million years. So there's a Goldilocks effect. That means if you want things to be just right for metals, this is an assumption, this is something that can be played with in the model. So if you have too little metals, then you might not form planets, as we saw with the 47 Tucani data with HST that Uffe mentioned yesterday. The second thing is that in metal-rich systems, it's clear that there are these, at least in some fraction of the stars, 5% was Uffe's number, that hot Jupiters can form. And if these are sort of migrating in or forming at small radii relative to the star, then that's going to make it inhospitable for Earth-like planets because the orbits won't be stable in the inner solar systems. So to account for the first bit, they adopt a kind of metallicity function, and it sort of peaks around solar metallicity. All right, so this diagram shows how this is time before the present. So this is now. These are different radii in the galaxy. So this is the central disk part of the galaxy, the center of the galaxy, and this is the outer part of the galaxy. And this is where the sun is lying. And this is the amount of metals on a logarithmic scale which have been built up as stars are born and stars die. So the sun is this dot here. So they sort of stick in a little bit arbitrary selection function here in metallicity, saying, well, if there's too much metals, you'll get these hot Jupiters, and that's not good. And if you don't have metals, well, then you can't form planets. So there's some kind of function here.
This is a really strong implication because it means in X billion years there will not be any more life forming in the universe.
Yeah, we'll have to move to we'll have to move, yeah. These parts of the galaxy will become the zone moves outwards, that's right. So the rise of complex life, this is just one number to keep in mind. It took about 4 billion years on Earth. We're just going to use that number as well in producing some of these things. The other thing they put in is the supernova wipeout factor. So in the central part of the galaxy, too many supernova. Again, it's sort of just boiled up. You don't really know anything much about that. So you can adopt a normalization relative to the Earth because obviously supernova over a 4 billion period have left the Earth. It's been fine here. So let's use that as our one and only point.
Which effect of a supernova explosion is affected mental to life or biostar?
Well, this is just hand-waving discussion in a paper. They're just talking about, too many gamma rays or too many neutrons or whatever coming, producing too high a flux on the planet, the surface of the planet, boiling away atmosphere. It's just something. It's not by no means explicit. Right, so this is the second plot they present. So you've got this is the supernova danger factor on a logarithmic scale, and time before the present. So this is black is bad, white is okay. So the Earth is in a region where, so that's the sun there, it's about 8 kiloparsecs per megaparsec. So it's in a region where it's relatively safe. This is the probability is dividing over 4 billion years. And going in too close to the galactic centre, it becomes unsafe because of the supernova. So that function is obviously quite loud. You could imagine it actually completely safe everywhere, and you could have a function which is a bit like that. That's something that could be covered. And the inner parts here, they're very vigorously forming stars at the centre. So actually, the start of the galaxy, there's lots of supernova there, and then it starts to run out of gas to form stars at all. So things actually quieten down in the centre of the galaxy. So what this produces is the galactic habitability zone. And so you've got this zone, and this is the time before the present, so that's now on the top. And this is the distance from the centre of the galaxy to the edge. So because of this 4 billion years, you say in 4 billion years on average you get multistellar light. So all stars younger than 4 billion years haven't produced interesting light yet. That's why you get this green zone up there. In the inner galaxies, too many supernovae for a while and they just destroy things. And then there's a zone here also where it becomes too metal rich in the inner galaxy, and out here this is too metal. And this produces an age distribution for life. So that's probably the interesting part there. That is that, if that's right, the life harboring systems represent stars, 75% of them are older than the Sun. The mean age is about 80 years. So we're relatively latecomers.
But that's a very small window, I should say, after the Big Bang. You have this time where you start coming life, and then sometime again after, it'll be over.
I guess it's, well, it might be 10 Hubble times or something. It's definitely refloating out, so it might be 10 Hubble times. Actually, eventually you'll have to worry about not having any, well, you have to worry about the stars going out and things like that. So you could just forget about that 4 GT thing and just say that maybe that's wrong, it takes 0 GT years for life to arise and suitable, even multicellular life to arise. And that would just push this green part all the way up to here. It doesn't change much elsewhere. And you will get an age distribution then which is much flatter. And instead of, in this case, you still get about 1 year age difference between the mean age of life systems and our own.
Yeah, but now the other way around. Previously it was older, now it's younger.
Oh, sorry, it should be, yeah, no, right, it's the other way around. And the other thing is that about 10% of stars that ever form, 10% of stars which ever form in the galaxy, in this model, could be bearing life. And then the other one's about 30. But the main point there is that there is a window, a certain selection window. You're down to about 10.
So the earthcomers or latecomers, what did we come just on time? Because one peak at one side and to the other side.
Sounds like you came just in time. They point out that the Sun is actually not in the middle of this function. So it hasn't been completely cooked up. That it's not entirely antiocentric.
But isn't that just a mistake for the assumption that we're average, so we should be average?
Yeah, we should be, but they just say we're not right down in the middle.
No, but if you
The
select it by
assumptions
the...
haven't been cooked. You could boil it up so that the assumptions would exactly be the same.
Yeah.
Okay, that's
Should I have questions and comments for this?
What is the nature of this tidal perturbation that you suggest that this tells the Oort cloud? I mean, if the Sun is oscillating in a harmonic potential, why something drastic happens just when it crosses zero? Is it kind of binary collisions with single stars, or what is the nature of this perturbation?
Sounds like I should go over to how can certainly answer that.
When you go after the galactic disappear of much higher density stars, unusual stars, they're more likely to be encountered.
So it's binary encounters.
Basically, binary encounters.
And then I have another question. I didn't understand how high metallicity increases the existence rate of inward magnetic hot Jupiter.
I think that's just an observational fact. That's how I interpret it. Would you agree with that? I mean, that 5% is the first that I've seen where there's a statistical number assigned to that. So it's not very many.
No, but I think that maybe one should dig more into the basis of this model, right? Because the assumption that you present that they give, right? It is that you don't have planet at low metallicities, and at high metallicities you form them too efficiently, so they destroy the whole thing. But I mean, this is an assumption, right? And I think there is nothing in the observations really that prove this. Right? The only thing we know is that there are 5% of the stars that have been searched in solar neighborhood that has these hot temperatures. And there is clear indication that the higher metallicity, the more there are of them.
Yeah.
And we know nothing about the majority of the stars. And therefore it's very early to conclude.
That's very up to the point there.
And maybe it's much better to form a very low metallicity because form only small kinds and maybe not strong.
Right.
There are all kinds of
Because
possibilities.
the 47 time data doesn't actually rule out cancer.
Absolutely
It's,
not.
it just says a 10 times lower limit for that.
Yeah, for the big ones, but I think it's small
Oh, okay,
ones.
yeah.
Only rules out white eagles.
This is a bit of a potential motif. So, I mean, we had about 10 years ago, we had this idea that sun actually were born at 4 or 5 kiloparsecs, and then it was not picked it up.
Yeah.
Is that theory dead, or is that something we still
Yeah.
name, or what?
There's much discussion. I don't think that anyone's proven it one way or the other.
Okay. Because that would kill this, right? Because then we would
No,
have
you
born
could-
at the
Well,
end of the
yeah, that would have to be taken into account. You could include that, and I would suggest including that they see that in.
If it's
that
true.
would be
I'm
important.
not sure if it's actually true that the sun is actually migrating.
I find it plausible, but I really think that most people don't.
I think that your first part is a very interesting example of how completely different fields are very relevant for astrobiology, and shows how many fields that play an important role before we can figure out these things. So suddenly you can combine the comets impacts and the asteroid impacts with measurements of the mass of the stars in the universe. That is very beautiful, and that also shows that we're still in the process of defining what is astrobiology, and this is a clear part of astrobiology. So that's a very important issue. Well, I think if I may comment a little bit more on this, because I think there's so many assumptions in it that one would say it's a little bit like Drake's equation has but it has a provocation of discussing various things based on something. But it will probably turn out to there is nothing of it that is correct. Right? Isn't that more or less also?
Yeah, I see it the same way.
Good, so if there's no more comments, we have a coffee break now until 11 o'clock.
Yeah.
So we stay, I think it's better we keep it in this. Shouldn't we keep something?
That's the fun way.
No, I think we will put it on the other side.